In this lecture, we're going to take a look at a new type of mathematical object which you may have never seen before, and that object is a vector. So whenever we're working in higher dimensional space, we want to distinguish between two main types of objects, what we call scalars. So a scalar is a real number, meaning a quantity like 0, 10, negative pi, 100, etc. So in general in mathematics, a scalar is a number, and in this course we only work over what we call real numbers, as opposed to complex or imaginary numbers. So when we say scalar, we're just talking about a regular real number. On the other hand, a vector is an object that has two properties. It has what we call a magnitude. We'll use that word a lot, and that's a synonym for the word length. So how long is the vector? And the second characterization a vector has is a direction. So a vector is an object with a magnitude and a sense of direction. We often represent vectors with arrows. So if we look at this vector over here, its magnitude is however long it is, and its sense of direction is what looks like northeast, so it's pointing up and to the right. If we draw a vector with an arrow like this, we will sometimes distinguish between the head of the vector, which is where the vector is pointing, and the tail. So the sense of direction for this vector is from tail to head. If I want to call this vector v for vector, I will by hand write v with a little arrowhead over it. So on paper, if you're writing down a vector, try to use this notation. In a textbook or in a paper, something like that, a vector is sometimes denoted by a sort of bold-faced letter. That's something that's very hard to do by hand. So by hand, use this arrow notation. And then a little later in this course, we're going to have an important family of what we call unit vectors. A unit vector, just to give you a quick definition, is a vector whose length is 1 unit long. And we will sometimes distinguish unit vectors with this kind of hat symbol. So if you see v hat like this in this course, that typically means a vector which is 1 unit long. Okay, let's take a couple minutes to distinguish between scalars and vectors. So on this slide, I've given you 5 concepts: distance, displacement, velocity, speed, and acceleration. These are all physical notions, and each one can be thought of as either a scalar quantity, so just a number, or a vector quantity, so a length and a sense of direction, or a magnitude and a sense of direction. So read through these 5 and decide what you would like to characterize each of them as. And then I'll go over whether in physics we think of these as scalars or vectors. Okay, so let's start with distance. If I say I live 15 miles from NC State, my distance to NC State is 15 miles. But you don't know if I'm north, south, east, or west, how I'm situated relative to campus. So when we say distance, for example, 5 kilometers, that's just a number. So our notion of distance is a scalar quantity. On the other hand, displacement describes how an object moved. Now, we don't use the notion of displacement in conversation as much as we do distance, but if I say that I've displaced something, the idea is I've moved it a certain amount in a certain direction. So in physics, whenever we talk about displacement, we're talking about not just how far we move something, but in what direction. So for example, you could move something 10 meters southeast. That makes displacement a vector quantity. Looking at velocity and speed here, it might actually be easier to start with speed. So if I say I'm driving my car 55 miles an hour, then I've described the speed. So that's just a scalar quantity. Again, in conversation, we usually talk about speed more than velocity. When you're talking about velocity, mathematically, what you're giving is a rate of change together with a sense of direction. So velocity is like speed coupled with a sense of direction. Therefore, velocity is actually a vector. Acceleration is the rate of change of velocity. You might think of acceleration as a scalar quantity if you're just thinking about driving a car or something like that, but actually acceleration is also going to be a vector quantity. And that's because the velocity, if it's changing so that you have non-zero acceleration, then your acceleration picks up both how quickly it's changing, a sort of magnitude, but also the direction you're traveling, because velocity is itself a vector. That sense of direction may also be changing. So I might be traveling east and then I turn and I'm northeast and then I turn and I'm going north, and acceleration will also pick up that change. So acceleration is going to detect how both the magnitude and the direction of the velocity vector changes. Let's talk a little more about vector notation. So I showed you earlier the notation v with an arrow over it, but there are other ways that we can denote vectors. So in particular, if I have 2 points, here this is 2 points P and Q in R2, and I want to go from P to Q with a vector, then we can denote that as PQ with a vector pointing that way. So it's like P is under the tail, Q is under the head, so we're traveling from P to Q. So this vector here is the vector PQ. We will often be interested in starting our vectors at the origin. So if I want to denote the vector that goes from the origin to point P, well, since origin starts with the letter O, we denote that OP with the vector over it. So this vector right here is the vector that starts at the origin and goes to P. In particular, this vector I just labeled is what we call the position vector for the point P. So the vector which starts at the origin and goes to some point is the position vector for that point. Therefore, OQ, starting at the origin and going out to Q here, that would be the position vector for the point Q. Let me consider a new vector v here. It's actually going to have the same direction and magnitude as PQ. So let v be this vector which points up 1 unit and 3 units to the left. That's actually the same as PQ. We will often write vectors with coordinates, and in this particular case, we'll say v is angle bracket -3, because in R2 traveling to the left is the negative direction, comma 1, because in R2 traveling up is traveling in the positive direction. So to the right and up, those are the positive directions for x and y respectively. To the left and down are the negative directions for x and y respectively. Now, in other sources, you might not see these angular brackets. We often use them in this course, but some texts would label a vector with just plain old parentheses, and that's okay. Another notation that you'll see a lot would look like -3 times I hat plus 1 times j hat. We're going to talk more about this notation, but this is the horizontal component, whereas j is the vertical component. So that's just a way to decompose a vector in R2 in terms of a horizontal component that goes with I and the vertical component that goes with j. Now I've said v is really the same as PQ, and let's talk a little bit more about that. So in this graph, I've given you a vector v over here in the first quadrant in R2. And then I've given you 5 other vectors, and the question is, which of these vectors graphed in R2 is the same as v? Now, what does it mean to be the same vector? Well, a vector is a length, or magnitude, and a sense of direction. So which of these 5 vectors has the same length and the same sense of direction? If it meets both of those criteria, then it's the same vector. Okay, so let's start here with the top left. This vector has the same direction as v, but it's half as long, so this is not the same vector. What about this vector here? Well, you can check. Let's see. This vector goes over 2, up 3. That's the same as v. In fact, let me go ahead and write that. V in component form is 2 because we go 2 units in the x direction, the positive direction, to the right, and 3 units up. That's the positive direction for y. So in coordinates, v is 2 units to the left, 3 units up. And you could also write this as 2i plus 3j. This vector has the same coordinates, so it's the same vector. This vector down here is pointing in the opposite direction. It's the same length, but it's the opposite direction. So this is not the same vector. Down in the 4th quadrant, you can check, let's see, that's to the right 2, up 3, that's the same vector. And lastly, this vector here, pointing from the origin out to the point P, which is actually the point 2, 3. That is also the same vector as v. And since it's starting at the origin and it's pointing out to 2, 3, the actual components of the vector, we say this vector is in standard position. So a vector is a length and a magnitude. It doesn't have an anchor point. You can draw the vector wherever you like to. But if you want to draw the vector so that the coordinates of the vector match where the head of the vector is, that's the standard position vector. Taking a little bit further, we can say it is the position vector for the point P. Okay, now that we've defined vectors and we've seen what they look like in R2 and shown how to represent them with coordinates, next we're going to do some vector arithmetic. We're going to look at operations on vectors through 2 different lenses. One is going to be algebraic, or in coordinates, and the other will be geometric. So we'll say what happens to the coordinates of the vectors under certain operations, and then geometrically what happens to the vectors themselves as we would represent them in space. Okay, so the first action that we're going to look at is stretching and flipping a vector through scalar multiplication. So that means multiplication by a real number. So algebraically in coordinates, if I have the vector LMN, here this is a vector in R3. Just for a little variety, if I take that vector and I scale it by a number c, so here c is just a scalar number, then how we compute that is we distribute c to each of the coordinates. So the first coordinate, the x coordinate, would be c times L, the y coordinate would be c times M, and the z coordinate would be c times N. Now this action of distributing the scalar to each coordinate happens whether we're working in R2, R3, or general Rn. So if I would like to take the vector 1, 3, which is actually the vector that's pictured here over to the right, and I would like to multiply it by the scalar -2, then that's going to be -2 times 1 for the x coordinate and -2 times 3 for the y coordinate. So the resulting vector would be the vector -2, -6. Okay, let's actually graph that vector over here to the right so that we can talk about visually what's happened to this vector. So we're going to graph this vector in standard position. The tail will be at the origin. And then to locate the head, we need to go -2 units on the x-axis, so that's 2 units to the left, and 6 units down in the negative y direction. Okay, so the head of the new vector, -2, -6, would be there. And this is that vector. So what's happened compared to the original vector? Well, the new vector is twice as long. So what we can say is if we compute CV, where here v is a vector, For us, typically that would be in R2 or R3, and C is a scalar. The result is the absolute value of C times as long as V. In other words, here it doesn't matter if I multiply 1, 3 by 2 or -2. In both cases, the result will be twice as long. If I took that vector and I multiplied it by 1/4, then the result would be 1/4 as long. The other observation to make is that the resulting vector that we graphed here is pointing in the opposite direction. What started as 1 positive unit to the right, 3 units up, got flipped to the left and down direction because our scalar C was negative. If C had been positive, we would have sketched 2, 6, and it would be pointing in the same direction. So the first observation to make is that C tells us how long the new vector is if we just look at the size of C, the absolute value of C. And then the second observation is if C is positive, CV points in the same direction as V. If C is negative, then CV points in the opposite direction. I left off one possibility here, and that's that C is 0. Well, if C is 0, then CV is the 0 vector. In other words, we would have just graphed CV as the origin. Okay, let's look at another vector operation. Given two vectors that live in the same setting, so either they're both in R2 or they're both in R3, then we can add them together. So again, we'll talk about this algebraically and then geometrically. So here I have the vector 1, 2, that's this vector v graphed over here on the right, and the vector 3, 1, which I've graphed here. To add these two vectors together, you add their x-coordinates and you add their y-coordinates. So v plus w will give 1 plus 3 for the new x-coordinate and 2 plus 1, or in other words, 4, 3. If they had been vectors in R3, we would add their x-coordinates, add their y-coordinates, and then add their z-coordinates. Okay, let's graph the vector 4, 3. So that's 4 units in the positive x direction and 3 units up, so that's going to land here if I start at the origin. So the result is this. Now what's neat about this is that we have two routes to actually get from the origin to v plus w using the vectors v and w. So first I could go from the origin to the head of w, and then from there go 1 unit to the right and 2 units up, which is exactly the coordinates of the vector v. On the other hand, I could start at the origin and go to 1, 2 by following v. And then from there I could go 3 units to the right and 1 unit up, but that's exactly the vector w. So when we do vector addition, this is how we think of it. If I'm doing v plus w, typically I would picture first going from the origin to the head of v, putting the tail of w there, and then going to the head of w. So it's like you connect the two vectors in that order. The order doesn't actually matter though, so you could do v and then w, or you could do w and then v. They'll both get you to the same place. And if you step back and look at this shape, it's a parallelogram. So we say that vector addition follows the parallelogram law. Okay, let's finish this lesson by doing one more operation on vectors, and here we're just going to focus on how to represent this visually. So we saw scalar multiplication and we saw vector addition. We combine them in order to make sense of vector subtraction. So here imagine A and B are two vectors, either both in R2 or both in R3, and I would like to compute B minus A. Well, how we can think of B minus A is we can think of this as the vector B plus -1 times the vector A. So by doing that, I've taken subtraction and replaced it with two vector operations that we've already seen. The first thing we'll do is take A and multiply it by -1, and then we'll do the sort of parallelogram law to add B to the result of -1 times A. Okay, so what is -1 times A? Well, the absolute value of -1 is just 1. So that vector will have the same length as A, but because the scalar -1 is negative, it's going to point in the opposite direction compared to the original vector A. Okay, so if this is my original vector A, I've just copied it over to the left. What we're going to do is just flip it so that it points in the opposite direction. This vector is now -1 times A, or we can just write -A. And now we're going to do B plus that. So I'm going to start at the tail of B, go to the head of B, and then attach the tail of -A there. Okay, so the vector B plus -A is going to start at the tail of B and end at the head of -A. So that was a geometric representation of what it would mean to do vector subtraction. That finishes this lesson on vectors. We're going to keep working with vectors, and we're going to look at more vector operations over the next several lectures. Thank you for your attention.